So we're going to keep going, and we're going to do one from 8.2. So let me put this one, 8.2. Okay, 8.2 changes. This is about one mean t-test. We looked at z-test in the last one. Now we're going to look at t-test. Okay, and why did we call it t-test? Okay, the reason we call it t-test is because when we're dealing with means and no population standard deviation, then we know it's a one mean z-test. Okay, so let's see what's going on. Let x be a random variable that represents the pH of our arterial plasma, which is acid in the blood. For healthy adults, the mean of this distribution is 7.4. Okay, again, I'm going to highlight it like I did in my last video. If you didn't watch the last video, I might, because I give you some tricks. So a new drug for arthritis has been developed. However, it is thought that the drug may change blood pH. A random sample of 36 patients with arthritis took the drug for 3 months. Blood tests show that the mean was 8.5 with a sample standard deviation of 2.6. Okay, when I copied this over, it lost a little x. So I'm going to break it down for you in just a minute and show you what every is. Use a 5% level of significance to test the drug's claim that there has changed either way the mean pH of the blood. All right, I'm going to do this. I'm going to put it in a different color because I'm going to use it later. All right, so what do I have in the problem? All right, I'm going to take some time and do it. Okay, population. Let's do the easier stuff too. Let's do your sample mean. So your sample mean, how do you know what to sample? Because it says here, a random sample of 36 patients took the drug for 3 months. The blood tests show that the mean was 8.5 and a sample standard deviation of 2.6. Okay, sample mean was 8.5. Sample standard deviation. Sorry, I can't spell this morning. Equals 2.6. Okay, population mean. How do I get that? It's up here. They said the mean should be this. It's what we expect all along. Okay, and then it wants to give me the sample size. Sample size is 36. And then level of significance. Okay, it says here 5%. Oops. Okay, level of significance is 5%, or if I can convert it to a decimal, it's that. All right, I have everything I need. I'm going to come back to that green in just a second, okay? All right, what's my level of significance? I'm just going to do that one right there. Copy and paste. There it is right there. It's given to me in the problem. It's not a big deal. Okay, so before I look at the things for the null and the alternative, again, I'm going to sort them. I've got an HO and I've got an H1. Remember, my HO is my null, and remember the null always has have the equal sign. So I'm going to do that right fast. So I put my mu symbol equals, and then it's going to equal the population mean, which is 7.4. Okay, that was easy. But now it wants to know the alternative, and it wants to know if the drug changed. It didn't say if it lowered it. It didn't say if it went over. It just says, did it change it either way? So the symbol for that, I'm going to put my mu symbol again, is not equal. So I'm going to put this here, not equal 7.4. Okay. I'm going to call this my original claim, and I'll show you when we go back why that's important, okay? All right. It wants to know, choose my null and my alternative. Well, here it is, right here. That's correct. Remember, null always has to have the equal. The alternative has the not equal in it. All right. So what sampling distribution are you going to use? All right. I was not given a population standard deviation, but I was given a sample standard deviation. Okay. When you have no population standard deviation, that means you're going to run a t-test and use the student t distribution. Okay, so that makes, that makes this answer a lot easier to get. Okay, so then I'm going to say student T, because the sample size is large enough. It is. It's over 30. And the population standard deviation is unknown. Okay, it's not normal. The reason it's not normal is, again, because we do not have the population standard deviation. All right, let's keep going down. What's the value of the test statistic? All right, this, I'm going to go back up to the top and I'm going to bring out my calculator. Turn it on. All right, so I'm going to go to stats and I'm going to go to test and I'm going to go down to t-test. I was given all the information. If I had to put the data in, it's like when you did t-interval and you put all the data in. I'm going to go to stats. Okay, what's my population mean? 7.4. What's my sample mean? 8.5. What's my sample standard deviation? 2.6. And you see how easy it is now that I have everything over here that I can just look at. Sample size is 36. My alternative, again, is the not equal. Okay, so it's flashing over the not equal. If I hit enter, look, then it flashes and it knows. And then I go to calculate, and then I know it did pick up the not equal. And I hit enter. Okay, so we're going to scroll down and put what I got. Oops, sorry. Come on. I was doing this earlier. All right. All right, so I'm going to put this right here. What is my sample test statistic? Okay, so my t-value is 2.538. So I'm going to put it here. T equals 2.538. All right, that was easy. All right, estimate the p-value. Why the heck am I going to estimate it when I actually have it? So the p-value is, let's go look at my thing. P-value is 0.0157. I'm just going to put it right here, 0.0157. All right, so I know the p-value is not greater than this. So I'm looking for the one that it's between, okay? It's not this one. It's not this one. It's this one, because if I did this, that's a true statement. Does that make sense? So that's how I did it. I would always solve for the p-value and then try to find where it fell in the scenario. Okay. All right, again, this is a not equals. How do I know it's not equals? Because, oops. All right, so it's not equal. Okay. Sorry, my computer's being weird again. So I'm going to go up. All right, so I'm given two tails. So it's this one, because you're given two tails because it's not equal. This would have been for a right tail. This would have been for a left tail, and that would have been for nothing that we do. Okay, sorry it's being so weird. All right, so let's finish. All right, do I fail or reject? Okay, so let's look at it again. Oops. My P was 0 point, let me go back up and see it. Let me see what I said. It was, yep, 0.0157. And my level of significance was 0.05. Okay, I'm going to take off these just to make my life easier. I'm going to add more zeros behind here. Oops, so I have the same number of decimals. Is 157 smaller than 500? Yes, it is. So I'm going to put my symbol in here. So since this is a true statement, I reject the null. If that is confusing, go back to the last video I did for 8.1. I talk about it in depth of how I did it. Okay, so I rejected the null. I'm going to go back up. Okay, so here I'm going to say my null was false and my original claim was true. So that means, yay, it was significant. This drug is lowering the acidity in blood. So I go back down. Okay. I rejected my null. Oops. I rejected my null, and it was statistically significant. Okay, so what does that mean? It means, yes, that it was lowering the drug and it's changing it. Again, why? I rejected my null, which meant that I was supporting the alternative. And the alternative wanted to know if there was a difference. Yes, there is doing a difference in it. I did say earlier it lowered it. It may not be lowering it, but it's going to be changing it. In stats, what we usually do is we run one of these kind of tests, a two-directional test to see if there's a change. If there is a change, we go to see what that change is. Because sometimes if you're doing less than and greater, that might be more work than to look to see if there was just a change.